Mute myself. Okay, welcome back. I'll give people a minute to pull up and see if there are any other questions before I start up again. Okay, so let's get started. So where am I? Okay. All right. So let me just summarize what I just said. If you have a group G and a parameter P given by X, lambda, and nu, associated to that is the involution of X, and that defines a real form of a real Cartan subgroup H, and lambda is an element of X upper star modulo 1 minus theta X upper star, and nu is in X upper star entered with Q upper minus theta, or can be the two equivalents can be taken to be in there. And all together, that gives you a character of H of R with differential 1 plus theta lambda over 2 plus nu. And that gives you a representation. Okay. Excuse me. So this last step, how do you get a representation from a character of a Cartan? That's a long and interesting story. And I want to start simply by just talking about the minimal printable series of split groups. Okay, so if you have a split group, if H is the it's some product of R crosses is the most split Cartan. Excuse me. There's a Borel B with this Cartan, and you can just look at the ordinary induced from B up to G of chi, where chi is a character of H of R. So the representations associated to Cartans, characters of Cartans in the case of the split Cartan of a split group is simply in parabolic induction from the Borel. And so that's what I wanted to look at first. So let's set G is equal to SL2R, and let's set I forget if I did this already, but I think I did, but I'll do it again just to be sure. Let's set parameters is equal to all parameters gamma of G with infinitesimal character rho. And as I saw before, there are 4 of these. And for P in parameters, and here they are. So as I said before, excuse me, well, now we understand a little bit more. These X's are giving you the Cartan involutions of the Cartans. So let's do, let's see, what is the involution of KGB element 0? And that's 1. So that is to say, this kg, the carton associated to this carton is compact because the corresponding theta is 1. And similarly, if you look at, if you look at the involution of KGB element 1, it's also 1. And if the involution of KGB element 2 is -1. Okay? Another way to get the same information is the following. Let's set x is equal to this kg. Actually, let's do it this way. Let's set p is the last parameter in my list. Okay, here's a question. In set parameters, is 1 equals rho by default? Okay, so Emil asked in all parameters gamma. Let's do a what type all parameters gamma. Excuse me. You handed a real form and a rational vector. So the rational vector is the infinitesimal character, and so I was doing this. I gave 1 here because rho of g is equal to 1. And, well, it depends on your group. So I'll do an example in a minute where you might want to enter something else. So there's, in some sense, the default is rho, but you just have to enter that. So I'll come back to that. So let's see. So we have this parameter p, and let's say x is x of p, excuse me. And let's set h is the carton class of x. And you can do print carton info of h. And it says this is a carton with no compact factors, no complex factors, and 1 split factor. That is to say, this is the split carton. Okay? All right. So now, so let's take a look. So these first 2 representations are associated to the compact carton because x is 0 and 1. So the 2 principal series are these 2. Okay. So let's set principal series 1 to be this parameters number 2. So this is a list of parameters. There are 4 of them, so they're labeled 0, 1, 2, and 3. So 2 is the second to last one, and 3 is the last one. So let's just see that I got those right. Okay, so these are 2 principal series with the same nu. The only difference is lambda. And so one of these is the spherical principal series, and the other one is the non-spherical principal series. And there's a row shift here, which takes a little bit of getting used to. What's the trivial representation of G? That's this one here. So what this is telling you is that the parameter for the trivial representation is it's the induced representation that has the trivial representation as a sub or quotient. That is to say, it's the principal series with infinitesimal character rho, and it's the spherical one, and that's the one where lambda is equal to 1. And you might have expected this to be lambda is equal to 0, but there's a row shift, which takes a little getting used to. So anyway, so these are the 2 principal series, and let's see. So the conclusion from what I just said is that PS2 is the spherical principal series with the trivial quotient, and PS1 is the non-spherical principal series. Both of these are at rho. Okay, so we can do a little bit of looking. Let's set I to be I of PS2. So this notation I means this is actually, let me not call it I, let's say standard. This is a standard module. It's a full induced from a principal series. And we can look at its composition series of the standard module. And this one, did I get this right? PS2. I'm sorry. What is PS2? I'm sorry, I got them backwards. PS2 is irreducible, and it's the non-spherical one. Sorry, I misspoke earlier. PS2 is irreducible and is non-spherical. So you can see there's these row shifts are never going to be easy. But the reason I know that is because I just got its composition series, and it said that it's irreducible, and this J stands for an irreducible representation. On the other hand, for example, if I show the composition series of I of PS1, this has 3 factors in it. And so let me give that command again on one line so it looks a little nicer. What this says is that this standard module, defined by this parameter, has 3 composition factors. And these are irreducibles, which is indicated by the fact that they're labeled J. And so this says that this standard module, I is a standard module is equal to J1 plus J2. It's the sum of 3 irreducibles. And of course, this is in, everything is in the Grothendieck group. These representations are not completely reducible. These are its composition factors. Okay, so let me do this one more time. PS2, 1, 2, 3. So again, this is saying that this standard module, if you break it into a sum of irreducibles, is a single irreducible labeled J. So this is an irreducible principal series. Okay. So let's look at a slightly different example now. So X is this KGB element. So let's set P to be the parameter X, and let's take the spherical one, which is given by rho. But now let's change nu to 3/2. Okay. So this is a parameter for a principal series with infinitesimal character 3/2. And if you look at the composition series of it, you see that, of course, it's irreducible. The infinitesimal character is non-integral, and so it's necessarily irreducible. Okay, so there's a whole family of principal series. You can say that P is the parameter X1 anything. Anything for nu, or you can, there's another family which is given by setting the lambdas equal to 0. And that's also irreducible. Excuse me. And another thing that you can do, if you wish, is the following. You can say, let's say P is this parameter 2 lambda nu. We can set P PQ to be the cuspidal data of this parameter. Okay, and what this is this is a parabolic, and P is a parabolic, and the Levy factor of P is this torus GL1, and P is this character of GL1. So we're not really learning very much here because it's a very small group and there's not that much going on. But anyway, you can extract the actual character of this carton this way by referring to the cuspidal data. Okay, so let's look at another example. Let's set G is equal to PSL2R. And let's set P to be well, first of all, what is G? G is a disconnected split real group with Lie algebra SL2R. So sometimes people get a little, the notation is a little bit confusing. What G of C is, PSL2C, which is to say SL2C modulo plus or minus 1. And the real points are disconnected. And that's denoted PSL2R. And another way to think of it is as the group SO21. Okay, so it's, worth looking at this group. It's a little bit different. Let's set parameters is equal to all parameters gamma of G. Oops. Sorry, I have to specify the infinitesimal character. Let's take it to be rho of G. What is rho of G, by the way? Rho of G is now 1/2, interestingly enough. Okay, so how many irreducible representations does PSL2 have at infinitesimal character rho? Well, it's just like SL2, except the one difference is the Weyl group of the compact carton has changed, and the number of parameters is 3. So let's look for P in parameters, undo this P. So these are the two principal series with infinitesimal character rho, and there's only one discrete series. So let's go back and look at the trivial. Let's set P to be the trivial parameter of G. And one thing that's helpful to keep in mind is that the trivial representation is always given by the KGB number, the maximal KGB number, and lambda and nu are both equal to rho. That's just a fact. So that's what we're getting here. Lambda and nu are both equal to rho. And what's the composition series of this guy? So let's look at the composition series of I of P. Let's see. So this is the induced representation for PSL2. How many factors does it have? Well, it has the trivial in it, and it has a single discrete series representation. There are only 2 factors. There's this J of x is equal to 1 is the trivial, and this J x equals 0 is a discrete series. All right. So, well, that's interesting. What is this other fellow? Parameter x is equal to 1. What are these 2 principal series of PSL2? Well, PSL2 is disconnected, and these principal series are, there's also the sign representation. So I believe you can ask this representation, the irreducible defined by this parameter P is finite dimensional, and in fact it's one dimensional. Let's set Q is the first element of the parameters. Whoops. 0, 1, 2. Sorry, I guess I want Q to be the second element of the parameters. Here we go. And is this representation finite dimensional? Sorry, Q. it's true. And the dimension of Q is 1. And P is not equal to Q. So what's going on here? These are two parameters. They're parameterizing an infinite dimensional induced representation, which has a unique irreducible quotient. And the unique irreducible quotient in the first case is the trivial representation, and in the second case is the sign representation. Okay? All right, now let's do another example. What if I said P is parameter KGB 1, let's say lambda is a half, and let's take nu to be 1. What can we say about this? Let's show the composition series of this standard module. It's irreducible. So even though nu is equal to 1, looks like it's an integer. Well, it is an integer, but it's not, this is not a reducibility point. Okay. All right, so I think that's enough of SL2. It's more helpful now to look at a slightly bigger group. So let's set G is equal to SP4R. And let's set the parameters to be all parameters gamma of G with infinitesimal character rho. Rho of G, by the way, is 2, 1. So how many representations does this group have with infinitesimal character rho? It turns out there are 18. And it's an interesting exercise to count them yourself. Excuse me. For P in, whoops, in parameters do. Let's look at them. So here are here are the parameters. So there are 18 of them, and the last 4 are have KGB element 10, and these are the ones where the corresponding carton is split, and these are the 4 principal series. So let me actually I should make a quick digression here. If G of R is split, rank n, how many the number of minimal principal series is what? Well, these are the characters of the split carton, R to the n, whoops, R cross to the n, and there's a sigma and an or lambda and nu, and up to the vol group, you can take nu. I forgot to specify the infinitesimal character. Let's say rho. You can take nu to be rho, and then there are 2 to the n choices. Oops, choices of lambda. Okay. So for SP4, there are 4. All right. Let's see. I got a question. Assume I can identify a representation by giving 2. Is there a way to get from the pair of KGB x lambda nu? Okay, so Letitia asked a sophisticated question, and let's see, I guess I can select this question. I'm not sure if people see it if I do that. I think they do, but when the software is recorded. So the answer to your question is yes, and but it's getting a little bit ahead of ourselves. I would like to talk about that, and I'm happy to talk to you on the side about that, or it'll be coming up in a couple of weeks. So let me punt on that question, but well, I'm not punting. The answer to your question is yes, and let's talk about that another time. Okay, so let's see, where was I? Oh yeah, so I'm doing SP4. So let's see, what do I want to do? I want to say set P is parameters bracket 14, I guess. So let's look at parameters 14, 15, 16, and 17. Okay. Actually, so let's put them in a list. Let's set principal series is equal to, I'm going to try and remember the syntax here. I'm not sure I'm going to. I think 14 colon. That didn't work. 14, 17. 14, 17. How about that? Okay, I'm forgetting the syntax. All right, but Mark won't be happy with me. But actually, I think what I can do is parameters. Sorry. So let's just do this the easy way. Let's set principal series is parameter. Excuse me. Parameters bracket 14. Parameters bracket 15. Parameters bracket 16 and parameters bracket 17. Very clumsy, but it works for P and PS2. Oh. Set P. I'm sorry. I wanted to make it an array. There we go. There we go. Okay, so there are my 4 principal series of SP4. How do you tell the difference between them? How do you understand what these parameters are? So each of these is telling you a character of the split Cartan. The new is always 2, 1, so it's always the same differential. And you're just talking about the 4 different parameters of Z2 cross Z2. So these lambdas, 2, 1, 3, 1, 2, 2, and 3, 2, those are running over x upper star modulo 2 x upper star. But still, which is which? So one of the main things that you can do is look at the tau invariant. So let's look at let's give this command. So here I'm running over these 4 principal series, and for each one I'm asking what is the tau invariant. And the tau invariant is more or less telling you exactly which these representations are. This one here where the tau invariant is, well, let's start with this one. This one here where the tau invariant is both 0 and 1, that means that this representation has big tau invariant, which is to say that it's a small representation. In fact, this is the parameter for the trivial representation. The opposite extreme is when the tau invariant is empty. That's an irreducible principal series, and 1 is the long root and 0 is the short root. So these 4 principal series can be distinguished by their tau invariants. So let's check, for example, let's set P is PS 0, and let's show the composition series of this corresponding standard module. This is the biggest composition series. This says that this standard module is the sum of the following irreducibles with these multiplicities. And notice that there's a multiplicity of 2 here. And well, this is the trivial representation. This guy right here is the trivial. This is the most reducible principal series, as you could detect by its tau invariant. If I look at the other extreme, if I look at the principal series number 2, and I show its composition series, this guy is irreducible. Okay. Now, another thing that you can do to examine these principal series is to look at the called status texts. Let's look at that. So This is, well, in this case, this information is more or less the same as the town variant, but it's useful to look at. What this is saying is that for this representation, the roots are of type R2 or R1 or Rn. And, well, sorry, for real roots, for a given representation, they have the simple roots, they have types. They can be R2 or R1 or Rn. And to be in the town variant is to say that this root is of type R2 or R1. That's indicated here. And these roots labeled Rn are not in the town variant. And notice that there's a difference between R1 and R2 having to do with the long and the short root. Okay, so here's a question. Could we also, let's select this question. Could we also look at lambda minus rho to get at the signed trivial characters on the disconnected part? The answer is yes. So why don't we look at that? So let's set P to be the trivial of G. And lambda of P is 2, 1, and it's absolutely correct that if I take lambda minus rho, rho of G, that the fact that that's 0, so the character on M is given by lambda minus rho. That is correct. Now the problem with that is it's not always that easy to interpret this. You know, if the group is not simply connected and so on, but anyway, that's correct. And so that's another way to detect that the trivial, excuse me, which of these is the trivial representation. Okay, so now another thing that you can do is you can look at the lowest k-types. So let's run over for P in these principal series. Let's I'm just going to give this command and then I'll explain it. Lowest k-type, highest weights. Let's print P. Whoops, P. I hope I got that right. Nope, did not. For P, do. Oh, that's too bad. I have some debugging turned on. What a shame. Okay, I'll have to fix that. But let's look at this very well. Let's see. I can scroll up here. So I'm sorry. There's a bunch of debugging turned on in the script at the moment. But the first parameter. Blah, blah, blah. Ignore everything except, where is it? Yeah, there's a lot of information here. But what I care about is this guy right here. This is the lowest k-type of this representation. It's 0. Excuse me. And the next one, it has two lowest k-types, which are 1, 0 and 0 minus 1. The next one also has 1, 0 and 0 minus 1. And then the last one has lowest k-types 1, 1 and 1 minus 1. Something bothers me about that. Somehow, I think David's going to correct me. I believe this doesn't look right. It should be 1, 1 and minus 1, minus 1. I'll have to check this. I have the debugging turned on for a reason here. So, but anyway, this is telling you about the lowest k-types of these induced representations. Certainly this first one here is, this is the lowest k-type, is the trivial representation. Okay, so let's look at a different example. Let's set G is SO3, oops, SO3 2. And set P is all. No, I don't think that works. So let's set parameters is equal to all parameters for by gamma for G with infinitesimal character row of G. How many parameters are there? 12 now. And let's look at them for P in parameters. So here they are. And again, it's these last 4 are the principal series. And so let's look at all of the parameters and let's look at their the tau invariants. I'm really only interested in the last 4, but I'll just print them all out while I'm at it. And so this is interesting. This is saying that the tau invariant of this parameter is 0, 1, and the last parameter is 0, 1. And that's because both of these are finite dimensional, which is to say one-dimensional. This group is disconnected. It has 2 one-dimensional representations. And there's an operation of tensoring with sign, which is a bijection of the, it's an automorphism of the principal series. It interchanges these 2 principal series, and it interchanges these 2 principal series labeled 1. Okay. So let's see. Let's set P is the last guy. Parameters bracket 11. And let's look at the composition series of the corresponding standard module. And let's do the same thing for number 8, 11, 10, 9, 8. It should look more or less identical. So let's see. It certainly does look almost completely identical. 0, 2, 3, 3, 4, 5, 6. I think the only difference between these 2 is probably, no, there are a few differences. But anyway, one of the differences is right here, this is a 3 halves and this is a 5 halves. And there's also some other, there's a 5 here. But these representations are extremely similar. They're both one-dimensional. It's a little bit hard to tell them apart. Let's look at parameter number 10. Let's see, what's the composition series of this thing going to be? It's smaller. It's not irreducible, but it is a has a less complicated composition series. Okay, so let's try. Let's see, what do I want to do? Well, let me pause there and see if there are any further questions that I can actually answer. So let's do a little bit more experimenting. Let's go back to SP4 and let's do a little experiment. Let's set P to be the trivial of G, and there it is. And what would happen if I, well, so for example, what if I set, set Q is equal to the parameter, and I suppose I put in a different nu. What is the effect of that going to be? Well, let's look. Nu is not dominant, but this is not, it could be made dominant. This is not a parameter that we haven't seen before. And let's see, is P equal to Q? The answer is yes. So the point is that the Weyl group is in the background here, and the Weyl group takes 2, 1, minus 1, minus 2 to 2, 1. And, well, what does it do to lambda? Well, as Emil pointed out, what really matters is what it does to lambda minus rho, which is 0, and it doesn't touch that. So the Weyl group relates these guys P and Q. By the way, there's a convenient function here. Let's set parameters to be all parameters gamma of G. Again, whoops, again, I forgot. I have to say rho of G. And I have a parameter Q. And I think that Q is found in this list of parameters that that I'm given, these 18 parameters that I'm given. And there's a way to check. You can say find Q in this list of parameters. Oops. Well, let's try the other order. Apparently, Q is equal to parameters, the 14th entry in the parameters, and that's correct. So the software knows how to tell when two parameters are equivalent. They don't have to be literally equal term by term. All right, so let's look at a different infinitesimal character. Let's go back to SL2 for a moment, and let's set P is the trivial of G, and let's look at P. And one of the things that's interesting to do is to well, I should illustrate another useful tool here, which is translation. And so here's my parameter P, and the infinitesimal character is rho. And this representation is finite dimensional, and its dimension is 1. And okay, so this is the trivial representation of SL2. Now, the translation principle is extremely useful. Let's set Q is equal to the translation of P to 2. So what this means is translate P from 1 to 2. And by translate, I mean apply a Zuckerman translation principle. Let's see what happens. Q, there's P, there's Q. What did it do? It changed nu from 1 to 2. So it changed the infinitesimal character from 1 to 2, but it also changed lambda. And that's a feature of the translation principle. You don't just change nu, you change lambda. Let's see, is Q finite dimensional? It is, and what's its dimension? This is now the 2-dimensional. And its infinitesimal character, of course, is now 2. So this translation principle is an extremely helpful way to move around, to change your infinitesimal character without changing the nature of the representation. So a reducible representation will stay reducible, and so on. So let's do another example. Let's set A is equal to, well, how do I do this? Let's look at P again. I think it's worth checking what happens if I set Q to be the same parameter. And let's keep lambda the same. Whoops, excuse me. Keep lambda to be 1. Excuse me. And let's set nu to be 0. All right, so let's pause and think for a second. What am I doing here? This is the previous line, I have the principles, the spherical principal series with infinitesimal character 1. And now I've changed nu, but I've kept lambda. So let's look at Q. It says Q is, well, it is what it is. It says it's a final parameter, and the infinitesimal character of Q is 0. So what representation is this? Well, I said you started with the spherical principal series at rho, and I kept lambda and I changed nu. So it's still spherical at infinitesimal character 0. This is the irreducible spherical principal series at 0. Okay, so I should pause there and emphasize. Let me say again what I'm trying to illustrate. So P is the trivial representation, and if I show the composition series of this corresponding standard module, it has 3 factors. Q is similar. All I did is I changed nu from 1 to 0, but I didn't change lambda. And if I look at the composition series of I of Q, it's irreducible. So that's not a bug, it's a feature. When you change nu without changing lambda, you change the reducibility of the representation. Okay, so let me just conclude this with an example. What are all of the irreducible representations of, say, SP or R at infinitesimal character 0? Well, let's think about that for a second. How can you get a representation of infinitesimal character 0? Well, you can take a principal series and you can set nu is equal to 0, but things can go wrong when you do that. So for example, well, you have to worry about lots of things, reducibility and so on. And on the other hand, if you have a discrete series at the other extreme, if you have a discrete series representation and you try and set lambda is equal to 0, well, that may or may not work. So I don't know, what's the answer? Let's set parameters is equal to all parameters gamma of SP for R at infinitesimal character 0. How many are there? Anybody want to take a guess? Let's see. 5. For P in parameters to print SP. Whoops. There. So that's interesting. There are 5. So notice nu in all of these is 0. Lambda is, well, sort of 0, but not exactly. So for example, this representation right here is the spherical principal series at infinitesimal character 0. And lambda is 2, 1, which is to say rho, but that doesn't affect the infinitesimal character because this is just telling you what the character is on the Z2s. And similarly here, you have some non-trivial lambdas. And then up at the other end, there are these 2 representations. Well, these are the 2 limits of discrete series. It turns out that SP4 has 4 discrete series, exactly 2 of which give you representations with infinitesimal character 0. So there's quite a lot of, this is much smaller than the number of representations at rho, and that's a general feature. In fact, the number of representations with infinitesimal character 0 is tiny. Okay, so let me just conclude with one last illustration of this kind of thing. Let's set P is the trivial SP4R. And one of the most useful things to do is to print the block of a representation. So this is the block of the trivial representation. It says parameter defines element 10 of the following block. That's right here. And this is the parameter of the trivial representation. The two roots are labeled R2 and R1, which is, as I was saying before, is telling you the tau invariant. And notice that this block has two principal series representations in it. These two, where over here, to look for a principal series, you look for one where x is equal to 10. So it's these two. And, well, there are 12 representations here. And I saw before that SP4 has 18 representations with infinitesimal character rho. Well, these representations are divided up into blocks. And so in particular, this block, it does not have all of the principal series in it. So where are the missing ones? Let's set parameters is equal to all parameters by gamma of SP4 at rho, excuse me, 1. And let's print the block of the last guy in this list. That's the trivial representation. But that's interesting. If you look at parameters number 16, this is a principal series, and this is in a block by itself. That's because this is an irreducible principal series. And if we look at number 15, I think that's also irreducible. And number, oops, I'm sorry, I misspoke there. Block of 15 is a smaller block. So how many representations do we have here? 1, 2, 3, 4, 5. That's the missing 5 representations. So SP4R has 3 blocks of size 1, 5, and 12, which gives you these 18 representations. This is all at rho. And I'll just do one last command, print block sizes, block sizes, I think it is, block sizes of P4R. This last row, this is telling you the number of the sizes of blocks of all of the different real forms of SP4. And this last row is the row for the split group. And like, as I said, it has 3 different blocks. Now I'll talk about blocks more another time, but to make a long story short, blocks are where the Kazhdan-Lusztig polynomials live. And a block is a singleton if and only if that representation is irreducible. Okay, so let's do one last command and call it a day. What are the block sizes for the split form of E8? Actually, let's set G is equal to the split form of E8 for what are the real forms of E8? There are 3 of them. There's the compact one, there's an intermediate one, sometimes called the quaternionic one, and the split one. And here you see the block sizes. This is telling you that the compact form, which is row 1, has exactly 1 block of size 1. The intermediate form has some smaller blocks, and then the split form has these 3 blocks. There's an irreducible principal series, And there are 73,000 in this block, and there's a block of size 453,000. And this group has 256 principal series. And it turns out that this one representation here is an irreducible principal series, and 120 of the principal series are in this block, and 135 are found in this block. And if I had a little bit of extra time, I'd actually print out these blocks for you, but I'll let you do that yourselves. Let me let me just finish up here. Where am I? Okay, there we go. So thank you, everybody. Thanks for the questions. I'll have to think about what to do next time. I want to talk about KGB and try and explain something about other kinds of representations besides discrete series, like, besides principal series, like discrete series, and work my way towards answering Letitia's questions. All right, thank you.